Okay, so the last little part with area, maybe one of the most important parts, I suppose, is going to be area between two curves. Okay, and we have a few different ways of looking at this. I'm going to preface it before I start with the method I'm going to primarily use, and the one that I've detailed here is maybe the one that just always works and kind of relies on the same steps and methods and understanding that we've been using in the previous sections for area kind of under the curve or between the curve and the axis. Okay, it relies on that same kind of idea and maybe follows a similar approach to some kind of questions we would have done in area, where we're maybe looking at kind of removing parts of the area or kind of looking at the negative space between different regions and that sort of thing. Okay, so that's kind of the main method. It's the main method I've laid out in the notes here. I'm also maybe going to talk a little bit about another method and identify where it works and maybe what the potential issues could be where it mightn't work. Okay, but it also, I don't want to not mention it because it is one that's be coming up a bit more often. And I suppose with that in mind, it definitely is a little bit easier in terms of some of the calculations here and kind of working out those calculations. It definitely does make things a little bit easier for us. So I'm going to look at kind of both of those, I suppose, and then see where that takes us overall. Okay, so area between two curves. If I have two curves as we see here, f of x and g of x, and if this is f, okay, and this is g, then we can kind of see visually that f is above g, okay, in terms of where the curves are. Obviously I've written the letter G higher, but the curve G is the red curve here, and for the most part that curve is below F, well, I suppose between the 2 points that I'm looking at, it is definitely below F. So if I'm finding the region enclosed between them, that is kind of a key point. Okay, so if I'm looking for the region enclosed between two curves, I need to know which curve is on top and which curve is on the bottom. And then to find that area, I integrate each function between the two bounds, a and b, where in this case a and b are the points of intersection. And I will subtract the area from f minus the area from g. Okay, and that will give me my points of intersection here. What we're really doing, in a larger sense, is if I have f, and I'm going to use this in kind of a green here, if I have f and I'm looking between these bounds here of a and b, so if this is b and this is a, if I'm looking at f and I integrate between a and b, that will give me this entire region here. Okay, the entire region that I have highlighted in green here, between a and b, down from the line all the way down to the axis, completely ignoring g altogether. If I then integrate g, okay, between a and b, that again should give me the area under that curve down to the axis. In this case, that would be the region that I'm covering in red here. So this is all the part under the curve down to the axis. Okay. Since we are subtracting the part that I've put in red here, all that will be left is the green part in the middle here. And that is the region that I was asked to find, the region between the two curves. So the real idea here of this method, I suppose, is find the area under the top curve, subtract the area under the bottom curve, and what should be left is the area between the two curves. Okay, that's the general, I suppose, understanding or idea that we're following here. And this method, I suppose, is going to work for us all the time, and it's always going to kind of be straightforward and maybe follows the method we've been doing the most, relying on that understanding of area. Okay, the steps I've laid out here: find the points of intersection. That's often really crucial because a lot of the time, obviously, that's where that area is created between the two curves. Sketch the graphs if not provided, generally are, but not always. Sometimes the roots may be relevant too. One of the curves could be below the axis, so that could also influence things. Find the area under each curve and then subtract the two areas, so the top curve minus the bottom curve. The key thing here is this last line. Okay, the key thing for all of these calculations, no matter what method we take, no matter what way we look at it, is knowing which curve is on the top and which curve is on the bottom. That's a really, really crucial thing in making these, in kind of being correct with your calculations here. We have to know which curve is the top curve and which curve is the bottom curve, because otherwise things kind of go a bit astray for us very quickly. Okay, so very, very crucial to know which curve is on top and which curve is on the bottom. Okay, so we'll have a little look at an example following that way, and then I might talk a little bit then about what maybe is the other method that's kind of appearing now. So find the area of the region B bounded by the curve f of x and the line g of x. Okay, so my line G here, my line F is my quadratic curve. I'm looking for the area between them, so that's going to be this area here. Okay, so based on that, F is on top, G is on the bottom. So it's going to be F minus G. Okay. So what I want to find is the intersection. So the intersection points, I'm going to put them equal. So F equals to G, x squared plus 8x minus 12 equals x minus 2. Okay, so 0 equals x squared minus 7x plus 10, answering that, x minus 5, x minus 2, so x equals 2, x equals 5. Okay, so let me see now, have I made a slight mistake there? No, x equals 5, x equals 2. Okay, and we can do a little look at my y values also. So g of 2 gives me 0, g of 5 gives me 3. So we're looking at 2, 0 and 5, 3 as my 2 points of intersection here. So this is clearly 2, 0, and this is 5, 3. Okay, that's my 2 values here. Okay, those are really the only relevant points here. I'm looking for the area between the two of them. We are going to the integral of f from 0 to 2 minus, so let's look at that first of all. So that's going to be the integral of minus x squared plus 8x minus 12 dx, which is minus x cubed over 3 plus 8x squared over 2 minus 12x evaluated at 0 and 2. So that's minus 2 cubed over 8 plus 8 times 2 squared over 2 minus 12 times 2. Okay, because I can see that every other part of it and the other side has an x part, if I'm going to be including, or say it's not from 2 to 0, excuse me, what am I doing? It's from 5 to 2. 5 to 2, of course, because I'm looking at the x values. Okay, so let me see, I'm going to change these out here and I will make the whole thing work again. So making this 5, of course. Sorry, that's my mistake there. Yeah, okay, we're back on track. I'll make this one 2. Okay, so I suppose that's the key thing as well, of just making sure you're kind of paying attention to the different bounds there. So even though we worked out the coordinates of the points of intersection, it's only the x values that I'm actually kind of focusing on here, or prioritizing. So let's find out or calculate these little kind of areas here. So this is minus 5 cubed over 3, which is a negative answer, plus 8 times 5 squared over 2 minus 12 times 5 minus 5 over 3. And then we also need to consider the same calculation for x equals 2, which is minus 32 over 3, which gives me an overall answer of 32 over 3 minus 5 over 3, which is 9. Okay, so 9 units squared. Okay, that's for f here. That's the region below f. I also need to find the integral for g in the same region. So that's x minus 2 dx. So that's x squared over 2 minus 2x between 2 and 5. So 5 squared over 2 minus 2 times 5 minus 2 squared over 2 minus 2 times 2. So that's going to give me, let me see, 25 over 2 minus 10, which is 5 over 2, minus 2 squared divided by 2, so 4 divided by 2, minus 4. 2 minus 4 minus 2, okay, which gives me an answer of 9 over 2. Okay, so the total area is 9 minus 9 over 2, so F minus G, okay, the area under F minus the area under G, which is going to be 9 over 2. 9 over 2 square units. Okay, and we can kind of see the idea in this kind of diagram here of what we're looking at. We're looking for the area under F, the green here, the area under the red here, and subtracted then to give me the blue area here between the two. Okay, so let's have a little look then at this other kind of method that I was talking about. So one of the things we'll notice here is that the regions or the bounds on the two functions are the same. So they're both being integrated between A and B. The other thing as well is that the functions are not swapping position at any point within those regions, within the region we're looking for. So there's no swap in position. The function on top remains on top at the whole time. Okay. One of our rules of integration is if I have an integral of f minus g between two bounds, I can split that integral out and integrate each of them separately. And really that's how we've been doing our integrals. So when we have a longer function, we integrate each part really separately. We just don't separate them out. We kind of just do each integral. But really that's what we're doing. Okay, we can separate out the integrals. So one of the ways I suppose that we can approach these questions is nearly to do that in reverse. So take the setup that we have here on the left and rewrite that by bringing the two functions together within this calculation. So subtracting the two functions and integrating them between those two values. Okay. I suppose just being careful as well here, maybe that we always kind of consider an absolute value here, because if all the regions are below the axis, there maybe is that potential. It's just, I suppose that's more just a general, just to always make sure that we end up with a positive value there, because we are looking for area. But this can prove quicker. Okay, there's kind of no two ways about it. This can prove to be a lot quicker. As I say, we have to kind of specify the functions must not switch position. Okay, or at the very least must not switch position within this range, okay, that we're looking at, because if they do, then that's completely going to affect our area. Okay, because then it will affect our integral. But obviously we could kind of adjust it in that way. But we're not allowed to have the function switch position within the range that we're looking at. Okay, but if not, this can definitely be a bit quicker and a bit easier to calculate here. So looking at it, I suppose, in this one here, I would be doing the integral from 2 to 5. The integral from 2 to 5 of minus x squared plus 8x minus 12 minus x minus 2 dx. Okay, just making sure we lay it out correctly as well, so that we don't just write down minus x. It's minus x but plus 2 because of the negative there. So it's really the integral from 2 to 5 of minus x squared plus 7x minus 10 dx. So it's nearly the kind of intersection function, okay, that you're integrating here. Really, you're creating a new function which has its roots at the points of intersection of the original function. Okay, so I suppose that to say that compared to what we have here, we are nearly creating a new function that, let me do that better, I'll use a different color that we haven't used. We are creating a new function essentially that has points of intersection, or has its roots as the point of intersection of these two functions, and which sets us up then to find this area in between here, which I suppose is kind of set up to be the same as the area between the two curves there. Okay, so evaluating this function then, just making sure that we're kind of content with it. It's a negative quadratic, so it will be kind of similar to this. We're looking for the region between there. Everything should be working out fine. Everything should be kind of content for us there. We're just looking between those two values. Those were the points of intersection of the original function, so they should be the roots of this new function. So we shouldn't have any areas above or below that we'd have to consider either. Okay, so looking at that then, that's going to be minus x cubed over 3 plus 7x squared over 2 minus 10x evaluated at 2 and 5. So evaluating that one, minus 5x cubed over 3 plus 7 times 5x squared over 2 minus 10 times 5 minus 2 cubed over 3 plus 7 times 2 squared over 2 minus 10 times 2. Okay, and let's evaluate those here for ourselves. So minus 5 cubed over 3 plus 7 times 5 squared over 2 minus 10 times 2 is 155 over 6. And then, oh no, cleared it. Oopsies. So 2 cubed over 3 plus 7 squared over 2 minus 10 times 2 is minus 26 over 3. So let's see if this works out the same then. Okay, and it does not. That's a bit of an issue. That's a bit of an issue. What have I done? I filled in something incorrectly here. Just try that again. Let me just try that again, because I'm not sure what we've done here. Minus 5 cubed over 3 plus 7 times 5 squared over 2 minus 10 times 5 is, there we go. There's my issue. I knew there was something wrong. Minus 25 over 6. Okay. Not sure what I typed in the first time, but let's go for it again. Okay, ensure we've got this one right. Minus 26 over 6. So minus 25 over 3 minus.
Okay, so if you're listening and comparing what I'm typing in to the calculator with what I have on my workings, I'm just typing in the wrong thing. And it took me far too long to figure it out. So it does give me the same answer though of 9 over 2. So moral of the story, does work. You can follow through the other examples then to kind of continue it out.
Okay, second example, let's have a look. So we're finding the areas above and below the x-axis. Find the area bounded by the line f of x equals 2x and the curve g of x equals x squared minus 2x. Okay, so they're kind of giving us a little hint here really on what they want us to do. So we're going to look for this area below the axis. Okay, and we're going to look for this area above the axis here. Okay, now there's kind of some added things to consider here really. So first of all, I'm going to look for the points of intersection. Okay, so that's going to be the first thing I want to find. So that's setting the two functions equal to each other. X squared minus 4x. So x equals 0, x equals 4. So this is 0, this is 4. Okay, so that's kind of the main region that I'm looking for here. I'm also going to find roots of g. And the roots of g, x squared minus 2x equals 0. So those roots I can kind of tell already, 0 and 2. So this is the value of 2 here. Okay, the main reason I want the roots here is that I can see that this negative region is the region from 0 to 2, and then the positive region is kind of all the region above that. So there's a little bit of work in setting this up if we want to calculate it in terms of the kind of regions and the areas above and below the axis here. So the red region here, which we'll maybe call A2, and then this region we can call A1, I suppose. So let's start with A1 here. Okay, to find A1, we are essentially looking for, okay, in terms of my curve, we are looking for the entire region below the line from 0 to 4. We are then going to subtract from that the region below the curve from 2 to 4. Okay, so we're going to subtract from that this region below the curve from 2 to 4 to give me that green region that I need inside here. So essentially this is the kind of purple region that I'm talking about here. Okay, so this blue region is the integral from 0 to 4 of f, which is the integral from 0 to 4 of 2x. Okay, that's going to be x squared, potentially, which is 4 squared minus 0 squared, so 16. Okay, so my blue region there, 16, straightforward. Okay, looking then at the purple region we have here, that is the integral between 2 and 4 of my quadratic, which is x squared minus 2x dx. Okay, so that's going to be x cubed over 3 minus 2x squared over 2, evaluated at 2 and 4. So that's going to be 4 cubed over 3 minus 2 times 4 squared over 2 minus 2 cubed over 3 minus 2 squared over 2. So 16 over 3 minus, let's fill in the other side, so 2 cubed over 3 minus 2 squared over 2, okay, minus 4 over 3. So that's going to give me 20 over 3. So the overall area I'm looking for here, 16 minus 20 over 3. Let's fill in that value. Gives me 28 over 3. Okay, so 28 over 3. Okay, so that's the region here. That's kind of my A1, if you like. Okay, that's the region above the axis. We also want to find the region below the axis, A2. That's the region between the quadratic curve and the x-axis. I'm expecting it might be negative. Okay, it should be negative. I don't know why I'm saying might. It is going to be negative because it's below the axis. It's the region from 0 to 2 of that same curve. What was it? X squared minus 2. Okay, so integrating that gives me x cubed minus x squared. Okay, 2x squared over 2, so just x squared, evaluated at 0 and 2. What's happening here? 0 and 2. So 2 cubed minus 2 squared minus 0 cubed minus 0 squared. Okay, so that is 8 minus 4, so 4. Okay, minus 0. Okay, no, I've made a mistake here, sorry. X cubed over 3, excuse me. X cubed over 3. So 8 over 3 minus 4. There we go. Okay, and how do I know I've made a mistake? Because it wasn't negative. Okay, so that's why it's important to have that consideration before we start. Okay, so negative answer there is what we expected. We didn't get negative straight away, so that's going okay. There's something wrong there, and I had forgotten my over 3 there. X cubed over 3, of course, and then x squared over 2. Okay, so it should be a negative answer, but the actual area itself then needs to be positive, so 4 over 3. So the total area is going to be A1, which was 28 over 3, plus the 4 over 3, which gives me 32 over 3. Okay, square or units squared. Okay, and again, I think I do have a little, oh, I don't know, I'm missing my diagram. Maybe I have it here. Just a little kind of diagram just to kind of consider what we're looking for here. So we were looking at the small bit under the axis, the larger part under the line, minus the bit under the quadratic, and that will give us that overall kind of area there that we wanted to find. Okay, now I suppose looking at this, we can apply or try and apply that second method again. Okay, so the idea here is that we are constructing a function which is basically the intersection function for these two curves. So 2x minus x squared minus 2x, which gives me 2x minus x squared plus 2x, so 4x minus x squared. So this is like the intersection function for these two curves. It's a negative quadratic, okay, which means that it's going that's going like this, okay, and its roots will be the points of intersection of the two curves that we're looking at. So roots 0 and 4. Okay, looking at our little sketch that we've drawn here, we've no reason to think that there's anything kind of that could throw this off. It's not going up and down. There's not two areas to consider. Straightforward, between 0 and 4, those are the roots. Makes sense with the kind of curve that we're looking at here. It is generally the area between the two curves that we're looking for. The fact that in the original curves that there's part below and part above doesn't really impact our intersection function here that we've created, because that function is just between 0 and 4. Okay, and again, it's kind of taking advantage of those rules of our integrals here. So we're going to integrate this function, which is just the subtraction of those two. So 4x squared over 2 minus x cubed over 3, just making sure we include everything correctly this time. So 4 times 4 squared over 2 minus 4 cubed over 3 minus, and that is all just going to work out to be 0 there. So let's try and fill it in. So 4 times 4 squared over 2 minus 4 cubed over 3, and get an answer of 32 over 3 square units. Okay, so you can kind of see there, compared to the work we did in the first section there, this is clearly a lot easier. Now, obviously, we have to be careful with constructing that kind of intersection function, making sure that there aren't any times where that crosses over, where the graphs change position or anything like that. But if that's not the case, then we kind of are set to go. And even though our original function had areas above and below the axis, we don't even actually have to worry about that as much. And partly that's coming from that idea that we've kind of described it as, it's that function nearly modeling the intersection between the two. So it will not go above and below because they don't cross over multiple times. And it's partly, I suppose, to consider that if I was to move both functions upwards, then all the area would be above the axis. But then subtracting the two, so I suppose what I mean by that is if I added 3 to f and 3 to g, and then subtracted the two, it would be f plus 3 minus g minus 3, which would still just be f minus g as normal. Okay, so the position of the two curves when we're finding area between the curves isn't actually going to impact the area as much at all. Okay, so it all comes down to really the approach that you're taking to it. So either this kind of longer but maybe more methodical approach, or we kind of look at subtracting the two curves and finding the area between them in that way. Okay, let me see, we have a few examples here, exam questions. I'm only going to pick out maybe one or two of those maybe to look at, because a lot of them kind of really fall into the same idea here. So these two functions f and g are defined for x values, real values. We're given the two functions, two quadratics. We want to find the coordinates of where they intersect. That means setting them equal to each other. So 2x squared minus 3x plus 2 equal to x squared plus x plus 7 gives you an answer of x squared minus 4x minus 5 equals 0, which is x minus 5 and x plus 1. So we get that x is 5 and x is a minus 1. Okay, we take a little look at our graph or our kind of diagram here. We consider, does that seem likely? And I suppose it kind of does there from the diagram. Because we're asked for the points of intersection, we really should be finding the other values that go with that. So we'll work out maybe g of each of those. So g of 5, if you sub that in, is going to work out, I'm just going to steal the answer here, 37. G of minus 1, if we work that out, is going to work out to 7. So my 2 points, minus 1, 7, 5, 37. Okay, I'm stealing the points there. It's not the main thing we're looking at. Okay, we're finding points of intersection, we should be able to do that. But it's the area under the curve I want to look at. I'm going to look at it both ways. We look at it in the two methods. You can kind of decide for yourself which you want to stick with. I suppose you need to know both. You need to know the normal way anyway, and then just decide if you want to apply this then for area between the two curves. Just bearing in mind that if you are, you need to watch out for if the curves swap position. That's kind of the main thing. So find the area enclosed between the two curves. Essentially, I want to find the area under G minus the area under F. Okay, minus the area under F between those 2 points, minus 1 and 5. Okay, that's really the sums that I'm going to be doing here. So we'll look at it separately, and then we'll look at doing it in the combined way. So let's go with G first, minus 1f of G. So what's my function for G here? X squared plus x plus 7. do. Okay, so let's look at 2. So g is x squared plus x plus 7, yeah. dx, that's going to be x cubed over 3 plus x squared over 2 plus 7x minus 1 and 5. So let's evaluate the 2. A lot of these sums end up being very, very similar to each other. Okay, you're basically following all the same methods. It was particularly at this point, really, it just becomes definite integrals. It's a lot of practice of your integration, making sure you're content with evaluating definite integrals. That's really what's going to come up a lot for it here. So let's have a look. So 5 cubed over 3 plus 5 squared over 2 plus 7 times 5 is 535 over 6 minus, let's change all of these to minus 1 now. Minus 1, minus 1, minus 41 over 6. Okay, so putting those together, 535 over 6 minus 41 over 6, or minus 41 over 6, so that plus 41 over 6. Ooh, bad sign. 96 units squared. Okay, let's have a go then at f. Okay, we know it's going to be the same idea again. Okay, integrating the other function this time. So the 2x squared minus 3x plus 2 dx. That's going to give me 2x cubed over 3 minus 3x squared over 2 plus 2x evaluated at minus 1 and 5 as before. So let's give that a go. 2 times 5 cubed over 3 minus 3 times 5 squared over 2 plus 2 times 5 minus, and the same sum then for minus 1. Okay. Now there is no doubt that this is longer. Okay, there's absolutely no doubt that this is longer, but it's just a matter of kind of bearing with it. So that's going to give me 335 over 6 minus 25 over 6, which works out to give me 60. So the total area then is 96 minus 60, which is 36 units squared. Okay, if we try and approach it the other way then, we've already found that we've already found that kind of intersection function. Sorry, the words were not coming to me there. So it's g minus f is what we want. So x squared minus x squared plus x plus 7 minus 2x squared minus 3x plus 2. That's going to give me an overall answer of minus x squared. That'll be plus 3x plus 4x minus 2 so plus 5 equals 0. We want to integrate this function between minus 1 and 5. Okay, bearing in mind that by definition we have created a negative quadratic function. I can see it's negative, which would have roots of minus 1 and 5. So we're now looking for this area between the two, which again we should be fairly okay to calculate. So that's going to give me an answer of minus x cubed over 3 plus 4x squared over 2 plus 5x, evaluate at minus 1 and 5. And we're going to get minus 5 cubed over 3 plus 4 times 5 squared over 2 plus 5 times 5 is minus 1 cubed over 3 plus 4 times minus 1 squared over 2 plus 5 times minus 1. Okay, I'm going to evaluate all of this then. So minus 5 cubed over, that's not going to work. Minus, oh no, that's not a good sign, is it? Minus 5 cubed over 3. How did I lose 5% so quickly? Right, we might have to wrap it up with this example, so, or else I will edit in more. We'll see what happens. So 5 cubed over 3 plus 4 over 2, 5 squared plus 5 times 5. Oh, sorry, I keep adding that in the wrong place. Plus 5 times 5 that all filled in correctly now? Yep, 100 over 3 seems to be. Minus, and we're changing all of these now to a minus 1. Minus 8 over 3. Okay, now that's going to give you 108 over 3. Okay, so 100 over 3 plus 8 over 3 is 108 over 3, which is 36 units squared. So same answer as we got before. We can see both ways lead me to the same result, slightly different method, maybe one less integral required by doing it on the right hand side way compared to the way that we did it on the left hand side there. Okay, so we can see the general method that we're following through. So area between the curves, it maybe is kind of the trickiest one that they can ask, and I probably will add in an extra example or two here to this one. I'm just kind of conscious that my thing is running the risk of leaving me. But just kind of following through the examples here, okay, identifying the area exactly that you're looking for and how do I need to combine the functions to get me to that area. Okay, those are kind of the key things really that you're looking for here. Really beyond what we've done here, I suppose you're following a lot of the same methods that we would kind of, I suppose, that we've seen in the questions here. You're following a lot of the same method a lot of the same time, okay? So like all the examples we've done here so far, you've basically followed the same method the whole way down for the area under the curve. Identify the area that works, remove the area that you don't need, kind of by integrating, know which function is on top and which is on the bottom. And that's kind of the key really that we're following through here. Everything else, I suppose, just ends up kind of being calculations, being integration, being definite integrals from then on really. There's nothing kind of extra beyond that. So let me see, I wonder, can I fit in another example before this abandons me? There's a few questions here maybe that were a bit trickier. We'll kind of fly through maybe this one as a last example because this was kind of a tricky one for 2023. So f and g are two functions. First of all, we're asked to find the values where they're equal. So x squared minus 2 equals x plus 4, x squared minus x minus 6 equals 0, x minus 3, x plus 2. So we get x equals 3, x equals minus 2. Okay, we were only asked for values of x, so we're content enough with that. We're now asked to find the area of the shaded region in this diagram below. Okay, it's the regions between these two functions for those two values of minus 1 and 2. Okay, so there's a bit of work involved in this one. Okay, depending on the method that we choose. And I suppose this is maybe where we really see the benefit or the difference between those two methods that we've identified. So one way that we can approach this is we can look at what we call area 1 here. And we're going to call area 1 this area above the axis. We can also look at area 2, which I'm going to consider this green area below the axis. And we just have to watch out for the small little area here, which I'm marking in blue. And it's a tiny little region that's not included between the two curves. Okay, it's under the curve, but it's above the axis. Okay, so we'll just have to watch out for that one. Area 1 is going to be the integral under f from minus 1 to 2. Okay, kind of straightforward enough. It's going to give me that entire kind of area there that I need. Okay, straightforward. And that's going to include the little blue part. Area 2 is the area from the other function g from minus 1 to, technically, looking at it here, up to this root point here. Okay, now I've marked that in. We can see that it doesn't actually go as far as 2. It actually cuts at its root there. So we need to find the roots of g of x by setting it equal to 0. And we get that the roots are plus and minus root 2. So we are really looking for the integral from minus 1 to root 2 here of g. And then area 3 is going to be the area from this root 2 to 2 of g. Okay, now technically, and I'll say this kind of even before we go any further, technically this region here will have a negative value. Okay, this region here will have a positive value. Okay, so if I was to do the integral from minus 1 to 2, I would end up with the same overall result. Okay, so if I integrated g from minus 1 to 2, I would end up with the area that I want. Okay, I would end up with the area that I want, because the distinction here, I suppose, is that I'm not looking for the area from -1 to 2. I am only looking for the area kind of from -1 to √2. So removing that small little kind of area, it is going to be helpful for me actually in terms of solving this question. I could find the overall area from F, or rather, I suppose even a better explanation, I could find the overall area under F from -1 to 2, work out the area from G from -1 to 2, which would include this small little part here, and then by subtracting that, I would kind of counteract the issues there, and the areas would end up working out for myself. But anyway, that's neither here nor there. I think that's more of a, if you'd stumbled into the right answer, you still probably could have got it right anyway. We're going to prioritize, I suppose, this method that we're setting up here. So let's kind of look at each of these calculations first of all. So we'll look at A1 first of all. Okay. So this is going to be the integral of f from -1 to 2. Now f is x plus 4. So that is going to be the integral of x squared over 2 plus 4x from -1 to 2, which is 2 squared over 2 plus 4 times 2 minus, and replacing that with -1's, 4 times -1. Okay, so that we see, I'm just going to kind of work through this here. So that's 10 minus -7 over 2, which gives me 27 over 2. Okay, so we get an answer of 27 over 2 there for our answer here. Okay, looking at A2, which is the area kind of below the axis here for G, so down from the curve up to the axis for G here, I'm expecting a negative answer that I will have to make positive. This is going to be the integral from -1 to √2 of x squared minus 2, which is x cubed over 3 minus 2x from -1 to √2, which is, of course, √2 cubed over 3 minus 2 times √2 minus -1 cubed over 3 minus 2 times -1. Okay, so working that out, let's see where that takes us. So that's going to give me an answer of -4 √2 over 3 minus 5 over 3. So -4 √2 minus 5 over 3. Okay, which means area 2 is 4 √2 plus 5 over 3. Okay, so important to just take the kind of positive value of that there for ourselves. Okay, so kind of positive value there. Looking at area 3 then. Area 3, tiny little area, same function. So from √2 to 2 of x squared minus 2, which we already know will evaluate to x cubed over 3 minus 2x, to be evaluated at √2 and 2. We can already see how we're kind of seeing some comparison there between this √2 and how it's included in both. In one is positive and one is negative, so maybe a lot of this is to do with how we bring it all together. So again, we're not going to worry about that too much though, because that's maybe getting into incredibly kind of not complicated, but just further level of understanding with it, I suppose. So 2 cubed 8 over 3 minus 4 is going to give me an answer of what, -4 over 3. We had that answer earlier, I think. And on the right hand side here, I suppose we've already worked this one out, -4 √2 over 3. Okay, so that's going to give me 4 √2 minus 4 all over 3. So putting it all together now, the total area that I want to get is going to be area 1 plus area 2 minus, I'm making sure that's absolute value, minus area 3. So 27 over 2 plus 4 √2 plus 5 over 3 minus 4 √2 minus 4 over 3. Okay, and I suppose what that's going to leave me down to then is 33 over 2. 33 over 2. Okay, 33 over 2 square units. Okay, so a tiny bit tricky, I suppose, and not a tiny bit, it's quite tricky there on that little element of getting rid of the area 3. Now, there are a few interesting parts really with this question here. Okay, there are a few interesting little bits to consider. I suppose what I had said already, which was maybe getting the area between just -1 and 2 of g of x. So we might want to consider maybe what that would do. So even just to kind of look at, what would have happened here if I'd looked at the area that way. X squared minus 2 dx. So let's just see. So we know already that's x cubed over 3 minus 2x. Evaluate at -1 and 2. That's going to be 2 cubed over 3 minus 2 times 2 minus -1 cubed over 3 minus 2 times -1. Okay, so that's, let me see, 8. So that's my -4 over 3 that we had earlier. And on this side, we have -1/3. Let me fill it in here. -1 cubed over 3 minus 2 times -1. We get 5 over 3. Okay, so -4 over 3 minus 5 over 3 gives you an answer of -3 here. Okay, so I suppose really here, then my 27 over 2 plus the -3, okay, or -3 if you like here, I would need to take this positive value from -3 and add that on. Okay, and that would give me my 33 over 2. So in the end, kind of does end up working out the same way. We would have to take that acknowledgement that that entire area for g is going to be negative, so we make it positive. What ends up happening really is that the little blue part that we had included in the calculation for f is deducted from the calculation for g, so it all actually ends up kind of working out nicely in that way. But again, that's maybe just something that would take a little bit more thinking through than we maybe would have time for if we were just looking at this in an exam. The other thing to look at then is that kind of other region, or that other kind of method that we were considering, which was just between f and g at this point. Now, important to consider here that we're not actually even looking for the points of intersection of these 2 points here, because we're considering -1 and 2, and that's not where they intersect. We know they intersect at -2 and 3. So I suppose important nearly just to look at that as well. F is on top and then g. So if we maybe tried to integrate f minus g between those values, and we'll just see. Okay, it's no harm for us to kind of consider, does it still work in this case? So x plus 4 minus x squared minus 2 dx. So I'm integrating, and let me see, plus 2, so 6 plus x minus x squared between -1 and 2. So again, we're essentially integrating here a cubic function. Okay, a cubic, or not a cubic, I should say, a quadratic function. We can consider the roots of that quadratic if we want to, just to help us with our sketch. Equals 0, so 2 inverse multiplied by root, so x plus, x plus 3 and x minus 2, of course, as we know already. So x equals -3 and x equals 2. Okay, matching up with, let me see, something's off here with my signs, I think. Of course, it's minus the negative x squared, of course. Okay, so we already know the answers here should be -2 and +3 from the calculation we've done earlier. That's the kind of intersection points. So that's maybe here and here. These are the roots of this new quadratic we've drawn. But what I'm looking for is actually between these 2 random other points here. But same idea. Okay, visually, kind of looking at the curve as it is here, we're maybe expecting, yep, this should work out okay. I'm just going to take it to the right-hand side of my curve here. So I know this is getting very complicated very quickly, and feel free to park it here. So let's integrate it and see, does it work? So 6x plus x squared over 2 minus x cubed over 3 minus 1 and 2. So 6 times 2 plus 2 squared over 2 minus 2 cubed over 3 minus 6 times -1 plus -1 squared over 2 minus -1 cubed over 3. Okay, and let's put all this together. Okay, at this point it's nearly just curiosity, I think, for us to see, and just be kind of content for ourselves. Does this method work? We've maybe identified the pitfalls that could happen. So we can see here there's no point where they're crossing over again. There's no point where things are kind of getting mixed up. Like where the position of the curves is changing or anything along those lines. So by and large, any of the kind of issues that we had identified don't seem to be present. But there's still always potential in these things for it not to work out. And I'm just conscious here that I'm kind of flying through a lot of different calculations here, so I just don't want to have made any mistakes if we can. And we're getting 33/2. So same idea again. So 3 different methods nearly that we've looked at there, yet all leading us to the same answer. Okay, I would say of the 3, the first one more in line with the methods that we've been taking for all of the other questions. You just have to remember that small little part with the blue. The second down here, maybe more of a if you'd stumbled into it, just to see that you still would have got the same answer even if you'd forgotten the little blue part there. And the last method then, I suppose, relying on that idea that if I'm finding area between 2 curves, I generally can subtract the 2 curves and integrate between the points that I'm considering, bearing in mind that the curves cannot be swapping positions. That's really the issue that can come in there. But besides that, everything else seems to work out perfectly fine for us, okay? So the main idea, area between 2 curves, generally always going to work out positive for us, okay? An important thing to consider as well. We always need to make sure it is, but in fairness, it generally does work out as positive. Considering either method, so either take it separate or consider it together, I would probably lean towards the separation method, but definitely taking them together does end up a lot quicker, as we can kind of see in the methods there.